We learned that the wavelength is governed by the wave speed divided by the frequency. Okay, that the wave speed is a property of the material, and then the frequency is a property of the source. Okay, that's still true. This is still a property of the material or the medium, and this is still a property of the source. All right, so in a string, the velocity is dependent on the tension in the string and the mass density of the string. If you make the string tighter, the velocity goes up. If you make the mass density greater, then the velocity goes down. The frequency is totally governed by the source. If I wiggle it faster, then the frequency is higher. If I wiggle it slower, then the frequency is lower. Okay, and the wavelength is what results. Now, on a string or in a pipe, when we're trying to create standing waves, there's an additional constraint on lambda directly from the situation. So let's draw an example here. If I have a string bound, fixed at both ends, okay, my string is of length L. All right. Now, if I were to make a standing wave here, I have to do it by like plucking it. So like on a violin, plucking a violin string, or on a piano, you tap the piano string, and bowing causes it as well. It causes the vibration by essentially plucking it repeatedly. But you can pluck it and cause the pulse. So that's the source, is how you pluck it. You know, if I pluck it in a certain way, but and then the tension in the string and the mass density of the string will say how fast that disturbance travels. Okay, the boundaries cause the reflections that create the standing wave, but guess what? The wavelength can't be just anything, because right here and right here, it's fixed. This point here can't be up or down. It's got to stay there at the equilibrium point. This point here can't be up or down. It's got to stay at the equilibrium point. So when I think about waves occurring on here, there's more constraints than just governed by this equation. Lambda itself is constrained by the boundary conditions here. Okay, so for this example, this is one in which the boundary conditions are the same on both sides, and we'll see that what results from looking at this as a string is the same for an open pipe or a closed pipe, meaning that so an example of an open pipe is our pipe, and it's open at both ends to the atmospheric pressure. A closed pipe, it's totally closed, and it might have an inlet here to cause a vibration in the air, but the ends of the pipe are closed to the outside pressure. So the important thing that's important for these cases is the boundary conditions are the same at both ends. We'll later do one where the boundary condition is different at both ends. That's commonly seen in certain musical instruments, wind instruments, where you can have a closed end pipe and then an open end on the other side. So that's where the boundary conditions are different. So we'll focus on identical boundary conditions for these three cases: open pipe, closed pipe, or a string fixed at both ends. Okay, so let's just go through this and see what wavelengths are allowed, and we call these modes. Okay, so first of all, the simplest way is to pluck it right in the middle, and I'd get one bump that would oscillate up and down. Okay, that's allowed because it's fixed at both ends. And my question is, what is the wavelength for that? Well, if I were to draw a dotted line out here in space, I could see that that would be one wavelength. Okay, I'm ready to repeat that cycle again. So that means this piece is half a wavelength, or my wavelength, lambda, is equal to 2L. It's double L. Okay, apologize for that little thing right there. So my wavelength, this line is just I'm going to make a table here. So for this case, my wavelength is 2L. Okay, well, let's draw the next simplest possibility. Still, it's got to be fixed at the ends, and so I can cause it to oscillate like that. So if I pluck the string here or here, I could cause it to oscillate like that, and that satisfies these boundary conditions. And so now that is a full wavelength, so my wavelength is equal to L. Okay, next case. Still got to get fixed, and so at the ends, and so this ends up being the next possibility. Fixed at both ends. I end up with 3 bumps. These would be oscillating up and down. And so now my wavelength is from here to here. And so that's 2/3 of the way across. 1/3, 2/3, 3/3. So my wavelength is 2/3 of the length. So we have 2/3 L. Let me do one more and then we'll see a pattern. The next easiest one is 4 bumps or 2 wavelengths. And so the wavelength is half L. Okay, we have the one wavelength that reaches halfway through. So we have half L, which I'm going to conveniently write as 2/4 L. Okay, that's the same thing as a half. And let me go ahead and up here say 1 L is the same thing as 2 over 2L, and 2L is the same thing as 2 over 1. Okay, so I can continue this. I've got 1 bump, 2 bump, 3 bump, 4 bumps. That's the first mode, second mode, third mode, fourth mode. But I can see that the first mode has 2L over 1, second mode has 2L over 2, third mode has 2L over 3, and fourth mode has 2L over 4. And so I can extrapolate, continue on, and say, for this case, lambda is going to be equal to 2L over M, okay, the mode. Okay, and I'm just choosing M. I could use N or some other letter to represent the mode. And so my mode in this case represents 1, or M equals 1, 2, 3, dot, dot, dot. Those are the allowed modes. I can't have anything in between. Okay, so the wavelength got constricted by these boundary conditions to allow only these modes, these wavelengths. So when you pluck it, what happens then? The material governs the speed of the wave. The frequency is the source. What it means is I'm only going to get a good effect if I pluck it in just the right way, or bow it in just the right way, or better yet, when I'm bowing it, many different frequencies could be caused, but the string only allows certain frequencies, only frequencies associated with this wavelength. So because music particularly, we often think of the frequency of the note, it's easier to think of then what are the allowed frequencies associated with this. So we just invert this and say F equals V over lambda, okay, and that indicates then that F is equal to V over this, so this is in the denominator, which means I'm going to bring the M to the top. I get MV over 2L. Those are the allowed frequencies to be played by this string, and it's based on the length of the string. And so in a piano, to get different allowed frequencies, you make the strings longer. You also change their density, make them thicker around, and make them tighter. That's what tuning usually is tightening this so the tension changes to cause a different velocity. So you can tune it to get what frequencies you want based on the length of your string and the tightness and density of your string. Same thing can be said for a wind instrument. You can make your pipe longer, okay, and you're fairly restricted with V because that's a property of the air, and so technically you could do this in helium or in water, and so you get a different material inside. But for our musical instruments, that is a little more restricted, and so we change L to affect that. And that's what like holes on the side of a flute do, is the holes force a node where the holes are, or force a boundary condition like these. And so if there's a hole right here, that means that that space right there has to also be constrained to be this boundary condition. So this is now our final case. Sometimes we'll put a subscript M on these to note that these are different modes, but now we know how to calculate them for a like boundary conditions. A string fixed at both ends, an open-open pipe, or a closed-closed